Okay, so this section 15.4 is on applications of double integrals. Okay. First, the most important one would just be basically physical properties of solid objects. Well, I guess they're not solid yet. These are two-dimensional objects. Two-dimensional object is called a lamina. But before we get into the more complicated two-dimensional case, let's go back and review the one-dimensional case. So I'm just going to do a bunch of little circular masses. Okay, I'm try and put these all on a line. Trying to decide where the center of mass would be. I'm gonna move this around a little bit. You're not gonna like me for this, I know. Okay, so we're gonna define all these points and masses. So let me go ahead and clean up a little bit here. Okay, so this is just like a number line here. So we'll call it X. We're just doing center of mass right now. So I think I'm going to put the center of mass really close to the right here. So I'm going to put a fulcrum here, which is the center of mass. And actually, if the values are all called X, then the center of mass tends to be called X bar, which is a statistics notation. For the average. But the center of mass is basically a balancing point. So I'll put that down. And of course, in lots of different mechanical applications, applications of design, center of masses are a really important property of an object or a system of objects. We know that, for instance, as planets revolve around the sun, they actually don't revolve around the sun. They revolve around the center of mass of the solar system. We tend to think of the sun as a fixed position, but its orbit wobbles. I should say the position of the sun wobbles as it moves around its own, around the center of mass of the whole solar system, which of course is very close to the center of the sun. Let's see here. These all are going to have positions. So let's give little positions x1, x2, and so on. So these are objects at these positions, and then they all have mass. So the masses are going to be m1, m2, and so on. Now, it's not true. The craziest thing about center of mass is that it's not true that the weight or the mass on the left is equal to the mass on the right. The principle for center of mass is that what are called moments on the left have to balance the moments on the right. And a moment is not mass, but it's going to be mass times distance. So the principle for center of mass that the sum, I'm gonna need more space, so let me move this. So the sum of moments on the left has to be equal to the sum of moments on the right. Okay, and that simple principle drives everything else that follows. So moment is equal to mass times distance. Okay, and I don't know, I think it was Archimedes who figured this out first, and he was the guy that kind of was working with just the whole notion of leverage. That, you know, these three little guys on the left can lift these heavy masses on the right if they have a lever that's long enough. And so that's kind of what it's the same notion of center of mass, that the masses on the left can balance the masses on the right if they have a lever that's long enough. So the lever is just the distance from them to the fulcrum, which is the center of mass. And the mass times the distance is what really allows them to lift these objects. Okay, so let's just go ahead and quantify these. The moments on the left have to be equal to the moments on the right. The sum, I should say. So let's look at these real quick. So now we can measure distances for each of these points. So the first point that I just highlighted, M3, that mass has a moment which is x bar minus x3. Sorry, the distance is x bar minus x3, and then you'd multiply by mass to get the moment. And then for the second mass, M2, then the distance is going to be x bar minus x2. Okay, and then of course for the third one, the distance is x bar minus x1. Okay. On the other side, we have two distances. The first one for this mass 4, the distance would be x4 minus x bar. And then the second distance for the fifth mass would be x5 minus x bar. Okay, so those are the distances, and we know that moments are mass times distance. So if you do the moments on the left, you would take the first mass, m1, times the distance, which is x bar minus x1,
plus the second mass, m2, times the distance, x bar minus x2, plus the third mass, m3, times the distance, x bar minus x3. That's the sum of the moments on the left, and this has to be equal to the sum of the moments on the right. So again, on the right, you have mass 4 at distance x4 minus x bar, and then the last mass, m5, at distance x5 minus x bar.
And what I want to do is move everything to the left. So watch this. We're going to do m1 times x bar minus x1 plus m2 times x bar minus x2 plus m3 x bar minus x3. Now I'll have, watch this. So I'm going to have a minus m4 times x4 minus x bar. And I don't know if you can tell these are all the same. And then minus an m5, and I'll have the x5 minus x bar. And this adds up to 0. Okay. And then what you do is just change the order of the subtractions. So one more time, last time. So you have an m1 x bar minus x1 plus m2 x bar minus x2 plus m3 times x bar minus x3. Now plus m4 x bar minus x4. So that's going to be thought of as a negative moment. So we're going to get over the notion of moments having to be positive numbers. Moments now can be signed. Last one plus m5, and we'll have an x bar minus x5. And of course that's 0. And then we want to write the general form that the sum of mi times x bar minus xi is 0. The sum of the signed moments, where I goes from 1 to n is 5. So the sum of the signed moments have about the center of mass, because you're measuring distances to the center of mass. But that sum always has to be 0. Okay, and then what you want to do is we're trying to solve for the center of mass. So we're just going to do a little distributing. So you could write this as the sum where I goes from 1 to n of mi times x bar minus the sum of mi times xi, where I goes from 1 to n. Okay. The x bar factors out of the first sum. So if you factor x bar out, you have x bar times the sum of the masses, mi, where I goes from 1 to n. So that's the total mass of the system right there. And this is equal to 0. So this would be equal to the sum of mi times xi. Now, the sum of mi times xi is going to be assigned distance to the origin. So these are moments to the origin. We usually say moments about the origin. And I think we say about because some of the masses could be to the left of the origin. We don't know where the origin is here. So these could be negative or positive. So these are signed moments. And it doesn't matter that some go positive and some go negative. We're not worried about that. Okay. And so the goal here was to have found a formula for the center of mass, which we've done. And so this is the sum of each mass times its distance for the whole system. Those are the moments about the origin, divided by the sum of all the masses, which is the total mass of the system. So we would write this as the sum of moments about the origin. So you have to, this sort of brings the coordinate system into it. Where 0 is. Can't tell you the center of mass until it knows where 0 is, basically. So you do the sum of the moments about the origin, and then you divide by the total mass of the system. And that's center of mass. Okay. Any questions about that? Now, we ought to be able to turn that into two-dimensional version. What we just did was a one-dimensional because everything was lined up on a single axis. But now I'm just going to make a region and call it R. And let's go ahead and come out with a little differential slice here. This point in the middle will be XY. Okay. The differential area is dA with mass. Now, I think in Math 180, when you were doing this, you called the mass dm. I don't know if you do that in 180. But I don't know that I want to use a dm. We have to bring in a density function. So this is what's called a lamina, which is just a, it's an object with mass, but no thickness, if you can figure that out. So just think of like a sheet of, sheet metal, piece of sheet metal or whatever. So it's really thin. Okay, so the lamina has to have a density function. So with the mass density, now I think they use a rho in our book, but rho becomes a problem later because rho is one of the coordinates in spherical coordinates. So we're going to be doing triple integrals, and then we're going to be doing centers of mass and moments of inertia for objects in 3 dimensions, solid objects in 3 dimensions. So that's coming very soon. And very often in 3 dimensions, your solids are best described in spherical coordinates. And in spherical coordinates, the distance to the origin is rho, which is a Greek letter. And the book uses, and they use rho for that, but they also use rho for the density, which I find very confusing if you have to integrate into spherical coordinates. So we're not going to use rho, we're going to use delta, which is a better go because it starts with the letter, density starts with a D. So the density is going to be delta of x, y, and then in parentheses, I'll just have you note that the book uses rho of xy for mass density. Okay, and that mass density is going to be mass per unit volume. So delta of xy is mass per unit. I said volume, but right now we're doing planar laminas. So this will be mass per unit area right now, and later on it'll be mass per unit volume. Okay. So, which is another way of saying, so now that we know, and I should say at the point x, y, so it's a variable mass density. So wherever you are, the mass density can be determined by this function, which I'm calling delta. And so mass density is mass per unit area. So mass would just be the mass density times area. So mass is going to be delta of xy dA. And then I guess I need to put a coordinate system into this. So if you've got some place to put a y-axis, we're going to need that. So I'll try and squeeze one in myself. Okay, and now there's going to be two coordinates, an x-coordinate and a y-coordinate for the center of mass. And the x-coordinate is the distance to the y-axis. So let's mark that. So we're going to be using distances to the y-axis, which are x, to find the x-coordinate of the center of mass, and distances to the x-axis, which are y, for the y-coordinate of the center of mass. Okay? So the moment to the x-axis should be the mass times the distance. Okay? So I'll say distance times mass. Okay, so the distance to the x-axis, unfortunately, is y. And the mass is delta xy dA. Okay. And the moment to the y-axis again, distance times mass, but now the distance to the y-axis is x times the mass, which is still density times area. Okay. Okay, now remember, the center of mass, you have to do the sum of the moments and divide by total mass. So let's do the sum of all moments to the x-axis. Well, we'll call this mx. Okay. And so you would just take a moment for one differential area. The moment is y times delta of x, y, dA. And you have to add these up, but you're adding over 2 dimensions. So this is a double integral over the entire region R. Now you have to remember that that's a measurement from the x-axis, but if you were to give it a coordinate, it would be a y-coordinate, okay, because you're taking distances that are vertical when you measure to the x-axis. Okay, and I can do the same thing for measurements to the y-axis where the distances are x. So moment to the y-axis, my, is the sum of all moments to to the y-axis. And it's the same formula, but the distances are not y, they are x. So double integral over r, x is the distance, delta of xy dA is the mass. Any questions? And now, so those are the moments to the two coordinate axes. And then just a reminder here, a center of mass is what we're looking for a two-dimensional lamina. The center of mass has to be the moments to the origin divided by total mass. So we're going to need a formula for the moment, for the total mass. So let's do that right now. So M will just be total mass. Okay. And of course, that's the easiest computation of all, because all you're going to do is just double integral the dm. So you're adding up mass over the entire region. So you don't need the distances to make it a moment. So you're just integrating over r, and then the mass is mass density times area. Okay, and then but the center of mass is two-dimensional. We're making measurements to each axis for an x coordinate and for a y coordinate. Okay, so center of mass is going to have an x bar and a y bar. Except for I don't want to put an ampersand. I'll do a comma because the center of mass is a point. Like that. Any questions? X bar is the mass, is the x coordinate of the center of mass, but you have to remember x coordinates measure distances to the y-axis. Okay. X is a distance to the y-axis. That's kind of one way of defining the x coordinate of a point. So you have to take moments to the y-axis and divide by the total mass. Again, the formula that we had up above here is the sum of the moments over the total mass. And maybe I'll put that down here. Okay, so it's the sum of moments divided by total mass. Okay, so, and that's this thing. Okay. And again, you have to use moments to the y-axis because you're measuring to the y-axis, which is an x coordinate. So that's why we call it x bar. And of course, there's a y bar. But the y coordinate of a point is a distance to the x-axis. So you have to do moments to the x-axis and divide by mass. So that's how you compute a center of mass. That's not easy or fun. That's 3 integrals you have to do. So now I'm looking for an example that we can do in about 14 minutes. Here comes. So this one says find the center of mass for the lamina R bounded between y equals x plus 2 and y equals x squared. With mass density at x, y proportional to the square of the x coordinate. Okay, and they give you, I don't know why all the books give you these proportionality statements for density. I don't know why they always do, but they all do. So you may as well see it. Proportional to the square of the x coordinate. So mass density, they're not telling you directly what it is, but indirectly, mass density is delta of xy. And it's not equal to the square of the x coordinate, it's proportional, which means you need a constant of proportionality. That's like two vectors that point in the same direction. They aren't equal, but one is a multiple of the other. Okay. We should probably graph the region. So you all know what y equals x squared looks like. Let's go ahead and try this out. Oh, there we go. Need to find out where these two curves intersect so that we'll know the limits of our integral. So this is our region R. So let's go ahead and solve the intersection. You always need to know, when you're integrating over regions, you're generally needing to know, if it's bounded by two curves, you need to know where the curves intersect. If it's a solid bounded by two surfaces, you generally need to know where the two surfaces intersect so that you can cast a shadow down into the xy plane and know what region you're integrating over. Anyway, for the intersection, you get x squared equals x plus 2. So x squared minus x minus 2 equals 0. This is x plus 1, x minus 2 equals 0. So x is -1, or x is 2. Okay, got it. So this is -1, and over here we're 2. And the picture's not great, but it is what it is. Okay, and I don't know if we need the coordinates here. This is -1, 1, and over here this would have to be 2, 4, right? So moments to the x-axis, let's go. Moment to the x-axis is a double integral over the region R of y times delta of x, y, dA. So you're going to have a double integral y delta of xy is just kx squared. And then we're going to go dy dx because the limits on y are curves. This region is what we call vertically simple. And I'll remind you, vertically simple means that vertical lines, when drawn, will go from one curve to the other and never change curves as you move the vertical line from left to right. And so the limits are on the on y are just the equations of the curves. So you're going to go curve to curve on the inner variable, which is x squared as a lower limit, and x plus 2 as an upper limit. So y goes curve to curve, and x will go from point to point, which is -1 to 2. Okay, I just want to pause for a sec and see if anybody wants to ask questions about that. Once you have one of these set up, the limits are the same on all three integrals because you're integrating over the same regions. Okay. You know, obviously you can bring the k out. I'm not going to evaluate this whole thing because we have 7 minutes. You go k times the integral from -1 to 2, and the integral from x squared to x plus 2, and you're going to have like an x squared y, dy dx. You do the math, and just trust me. Let me find it. That one is horrible. It comes out to 18k over 5. Looks so simple, but I almost took a whole piece of paper to do that one. Okay. My double integral of x, same region r, x times density. Like that. And of course, that means we're going to do an x times kx squared, and then dy dx. And x is going to range, sorry, y is going to range from x squared to x plus 2. So as I say, the limits are always the same on both integrals. Okay, and then y would go from -1. Sorry, those are limits on y from x squared to x plus 2, and then x goes from -1 to 2, like that. And so you're going to have a k double integral of just x to the third. Okay, so k times x to the third, and then you're going to have a dy and a dx. Y goes from x squared to x plus 2, and x goes from -1 to 2. And when you do the math, this whole monstrosity comes out to be, no wait, this is my, so let me find it. And as I said, normally I go through the painful math on all this, but so we do this one. Oh, that one's, wait, yeah, my. I think I got these backwards, dang it. I'm so sorry, guys. So mx comes out to be 18k over 5. Sorry, my is 18k over 5, so I've got the answer switched on these. It is mx that comes out to be, see if I can find it. So mx is 537k over 140. You know, I've said it, I'm just going to double check, make sure I'm not screwing this up. 537K over 140, horrible, horrible. My, 18K over 5, that's correct. And then let's just do M real quick. Okay, so M's the easy one. It's not, but M is just a double integral of the density function. Okay. Over the same region. So here we'll put in a double integral of kx squared. And then dy and dx. And same limit, so y goes from x squared to x plus 2. X goes from -1 to 2. And doing the math, that comes out as 63K over 20. Okay. And then the center of mass, so just to remind you that x bar is my over m. Gotta be careful with that. Everything's kind of backward. So my over m. My was 18K over 5. M is 63K over 20. Okay. These typically reduce pretty nicely. So this one's this boils down to 8 over 7. The k's cancel. So this is approximately 1.1. If you just want to know where it is. And then the y bar is mx over m. So the mx was the 537K over 120. And m is the same, it's 63K over 20. And you can see lots of things that would simplify, and it comes out not nicely. It comes out as 179 out of 147. Can you believe that? That's just bad news. And of course, simplifies to 1.2. So that's the center of mass, 1.1, 1.2. Now it looks way off. 1.1, 1.2 is going to be over here. Now I've drawn it in like this. So that's the center of mass. Actually, it's off a little bit. I forgot where 1 is. So if this is 1 right there, 1.1, 1.2, it's going to be right about here. Okay, and it looks really out of position, but remember this thing gets heavy as x increases. So this thing is really heavy on the right side and it's not heavy on the left. So that's why the center of mass is so out of whack. And plus my picture is probably not that great. All right, that's all we have time for today. So we'll do more of these next time, and I'll give you a little more details on the next example. All right, guys, I'll see you. Okay, so again, we're talking about circular motion. We've got a mass that's moving in a circular motion. The radius of the circle is r, and the angle of inclination is theta. And we know the relationship between the arc length, which is the distance being traveled, and the angle is that s is r theta. And recognizing that the object is moving, that s is actually a function of time and theta is also a function of time. And if we're interested in speeds, then we have to do, as you remembered, that speed is ds over dt. But this would be, because r is constant, you'll just say this is r times d theta over dt. Okay, and d theta over dt is usually indicated by an omega, so that's called angular velocity, even though it's not a vector. Okay. And then if I want to show you, talk about kinetic energy. So, and talk about how moments play into kinetic energy. Okay, so first of all, Ke for kinetic energy is 1/2 m times v squared. Now, v is really meant to be speed, so maybe I'll use a script v because that's sort of standard. So let me back up a little on that, and let's use a script v, just so that we sort of understand that's a scalar. Okay. So that's kinetic energy, and mass is m. Okay. We usually, when we talk about this in terms of circular motion, we could say this is 1/2 m, and then the velocity is equal to r times d theta over t, which is also known as r omega, where omega is the angular velocity. So this velocity could be r omega if you're moving around a circle. So you get r omega squared here. Okay. And 1/2 m times r squared omega squared. Okay, so m times r squared is a mass times distance squared. Okay. Whenever we multiply mass by some power of distance to a power, those are called moments. Okay, so what we refer to as the first moment is just mass times distance. Okay, and if I had a word for that other than moment, I would call it leverage, maybe. Although moment of inertia could also be thought of as leverage as well, depending on, you know, if you're thinking about torque or whatever. But mass times distance usually is what I think of in terms of leverage. The second moment and of course, first moment is mass times distance to the first, right? Second moment would be mass times distance squared. Okay. And so mass times distance squared is called the moment of inertia. Okay. I guess while we're at it, we could put in a 0th moment. It makes me feel like if you want to be complete, the 0th moment would be what? Yeah, just mass, right? So this would be mass times distance to the 0th power. So this is just mass. Now, I always kind of wondered why they referred to this, the second moment, and why the word, yeah, you guys are all good with that. I always wondered why the second moment uses this term inertia in it. It's related to the 0th moment. Does anybody have a measure for inertia? How do you, I know what inertia is, sort of the reluctance of an object to move or to be stopped. So how do we quantify inertia? Okay, objects with inertia don't like to be moved. But once they're moving, they don't like to be stopped, right? That's what inertia is. How do you quantify inertia? Now, I don't want rotational motion here. So if you see most of these, here this says for rotary motion. For rotary motion, inertia is quantified such and such. Now, we don't want rotary. How we measure inertia? The very first sentence, this is good. There are two numerical measures of the inertia of a body. The first is its mass. So mass itself is inertia, okay? Again, that just is the resistance to some force, meaning it doesn't want to be pushed. It doesn't want to be stopped by a force either. So that's just inertia. And the mass is the inertia, which is the 0th moment, okay? There's another numerical measure that I don't know if I see. It's resistance to the action of a torque around an axis. So inertia is resistance to a force. The other inertia is moment of inertia, which is resistance to a torque on an axis of rotation. Okay, so let's go back to our notes here. So mass is the same thing as inertia. Okay, mass is how we quantify inertia. Okay. Moment of inertia, this is, let's give a letter for moment of inertia. Let's call it I. Okay, that's the second moment. And it's mass times distance squared. So if you look at kinetic energy for a rotational object, it's 1/2 mass times distance squared, which is moment of inertia, times omega squared. Okay, so I here is the moment of inertia. Okay. M up above is just inertia. So moment of inertia is analogous to mass, except for it's related to rotational motion. Okay. And if you think about it, it's mass times distance squared. So if an object has a great deal of mass, but it is very small and you rotate it about the center of mass, then the distance is 0, okay? And when we talk about distances, we're talking about distance to the center of mass. So if an object is rotating around its own center of mass, then the distance is 0. So its moment of inertia is 0. Okay, it doesn't take any, takes very little energy to rotate small objects around their center of mass. Okay, now when you move the object away from the axis of rotation, it takes more energy to rotate it because the distance is getting large, right? The kinetic energy is 1/2 I omega squared, and I is distance squared times mass. So the amount of energy gets really big when you rotate things around an axis that's away from the center of mass. So the moment of inertia is a measure of inertia that's mostly related to how the object is distributed across some axis of rotation. Okay, it's more about distribution of mass relative to an axis of rotation. So moment of inertia is analogous to inertia. It's like mass, but it's mass measures inertia for linear motion. Moment of inertia measures inertia for rotational motion. Okay, so just to remind you what the formulas for moments are, coming back up here, where are they? So here are the formulas for moments. Okay, mass is mass density times area. These are two-dimensional objects right now. Okay, so mass, again, is mass density times area, but then distances are distances from either the x-axis or the y-axis. And by the way, y is the distance from a point to the x-axis, and x is the distance to the y-axis. Okay, but if we take these formulas, all we have to do is change them to distances squared, and they become formulas for not the first moments, but the second moments, which are the moments of inertia. So we're going to go ahead and grab these and put these down here. Okay. So this is all a question of which axis you're rotating about. Change the distances to distances squared. Okay. And these are I for moments of inertia. But it's always with respect to an axis of rotation. So if you're rotating a mass around the x-axis, then the distance to the x-axis is y from any point. And the distance to the y-axis, I apologize. The distance from the x-axis, this should have an x here because you're doing moment of inertia about the x-axis. You're rotating around that axis. The distance to the x-axis is y, so we have to use these y distances for the moment about the x-axis. And the distance to the y-axis is x for rotation around the y-axis. So those are the formulas for moments of inertia, okay? If you want to rotate about the origin, let's draw a little picture here, maybe off to the side. So I've got my coordinate system. I've got some region here with mass. Let me make a feather pen. So I've got a region here that's got mass. So this is region R, okay? And you can take a point and think about the distance to the y-axis or to the x-axis. Okay, so x is the distance to the y-axis and y is the distance to the x-axis. You can also rotate around a point. So this distance would be r, and you know that r squared is equal to x squared plus y squared. I0 would be the moment of inertia for rotation about the origin. So this is moment about the origin. I should say moment of inertia, my bad. About the origin. So you're just taking this region and spinning it, or at least trying to spin it, and its moment of inertia is its sort of its resistance to any torque that you apply to it. Okay, nothing likes to be moved if it isn't moving. So its inertia is, well, we said it's r squared, the distance squared. But r squared is x squared, is x squared plus y squared. And then you multiply by mass, which is mass density at each point times differential area. Okay, and then it's not too big a stretch to see that you actually don't have to do much. You don't have to evaluate that integral if you have already done the other two. So this is actually ix plus iy. Super convenient. Little Pythagorean identity there, because you're using distances squared and right triangle and all that stuff. Okay, so maybe just a little more labeling, just to make sure everything's clear here. So Ix, that's the moment of inertia about the x-axis. And of course, the other one is the same, but you're rotating about the y-axis. Okay, so those are just formulas. And again, the moment of inertia is used to compute the kinetic energy, but it's mostly just, when you design a motor or any object, oh, was frozen, but we're back on, sounds like. What are the pluses? I'm gonna pause for a sec. Okay, so like I say, moments of inertia are super important when you are designing an object that has some rotational property about it. The distribution of mass about the axis of rotation is what defines the moment of inertia, and the distribution of mass goes directly toward the amount of kinetic energy in a motor as it spins, and the distribution of mass is described by the moment of inertia. So we're thinking about the moment of inertia not only as just sort of this resistance to a torque on an object as you try and turn it, as you try and spin it, but it's also a description of how the object is distributed around an axis of rotation. And the wider the distribution about that axis, the more energy it takes and the more inertia, more rotational inertia it will have. Okay, so you'll see, those of you who take physics and go on into engineering, you'll see how important moments of inertia are. Okay, so here comes a pretty crazy problem. Okay, so this one says give the moments of inertia for the region, I'll say the lamina, inside x squared plus y squared equals 2y, but outside x squared plus y squared equals 1. Okay, with mass density inversely proportional to the distance from a given point to the origin. I'll just say the distance to the origin. Okay, so there's a lot going on here. We probably should get a graph. So just remind you, for x squared plus y squared equals 2y, one thing to note is that that's probably best in polar coordinates. So you can say r squared is 2r sine theta. Okay, and then insist, I'm not interested in r being 0 here. So if r is not 0, then you can say r equals 2 sine theta. So that's the polar coordinates form of that equation. But I still, maybe you know what that is and maybe you don't. So it's easiest just to do it in rectangular coordinates to know what this is. Maybe you know, x squared plus y squared minus 2y, there it is. And then we're going to complete the square, so add 1 to each side, like that. And then you see x squared plus y minus 1 squared equals 1. So that's a circle, radius 1. Centered at 0, 1. Any questions about that? The other circle, x squared plus y squared equals 1 means r squared is 1 and r is plus or minus 1, but we'll just go with positive 1 because I don't want a negative radius on a circle. Okay, any questions out there? Just two circles, inside of one and outside of the other. So let me see if we can draw this here. I'm going to try and get the coordinate system centered properly. I think that's what I want right there. So your 0, 1, I'll just put a 1 there for the height, the y coordinate. And it says it's inside the top circle, but outside of the bottom circle. So we're shading above and inside of the top one. Oops. I'll zoom in. So that's our region. I don't know if I gave it a name. We'll call it R. Okay. So I've got the region pretty well. Let's go ahead and put equations. Actually, I'm going to do slices. We talk about radial slices here. So I was doing this with sort of a gray pen last time where I was drawing slices out from the origin for graphs and polar coordinates like this. Okay. And so I'm interested in this lower limit and upper limit on those slices, and inside I usually put like a little rectangular differential area. And I think about, okay, what are the coordinates of that point? And we're going to move that point around as we try and cover the whole region by it. Okay, and maybe think about theta also. Let me put that in. So this angle here is going to be theta. But while we're at it, there's going to be two other angles. This is crazy. See, I need to know where the region starts. So I'm going to need to know an angle for theta here. And I also need to know where it ends. So an angle for theta over here. They look like pi, you know, they look like pi over 4. But I'm not so sure. Maybe they look like pi over 6. Not sure. Okay, but on the outer limits for r, r is 2 sine theta on the outer limits. So I'm going to zoom in on this again right here. R is 2 sine theta. And on the inner limit, of course, R is 1. I'll just draw an arrow for that. So there R is 1. Okay, so how y'all doing out there? So I know the limits on, again, the hard part is setting up the limits for the integral. And the inner limits go from one curve to another always. And the outer limits go from a point to a point. Now, the points right now are values of theta. Okay, so let's do the intersection of the two curves. So I'm going to do that, continue to do that in gray. So down here for the intersection, that will be where 2 sine theta equals 1. Oh, this is super easy, right? 2 sine theta equals 1, where I touch the two curves together. So sine theta is half. So theta, come on, save me, you guys. What's theta? Yeah, pi over 6. Kind of looked like it. And what's the other one? Yep. 5 pi over 6. Way to go. Okay, so I know my limit. Basically these 4 statements are the limits for integration. So if you can set that up, that's a hard problem. I would feel bad about putting that on an exam. If I did that one, I think, okay, there's a hard problem. Okay, where's the easy problem? Find something easier. Don't do all hard problems, kind of thing. I'm gonna pause for a second while you guys think about questions you might have. Okay, so again, this is all just analysis. We haven't even done computations yet. The computations are almost a side issue. Much more importantly is just your ability to kind of pose the problem correctly. So for example, we can do the moment about the x-axis. So moment about, let me switch colors real quick here. So the moment about the x-axis, the formula, oh, we didn't set up, we haven't done the the formula for the density. But let's see what we can do here. So moment about the x-axis is a double integral over the region. We have to do distance squared. Now the distance to the x-axis is y. Distance squared times mass, which is the mass density at xy, dA. Okay. Let's just think about this. We can do a lot of this in polar coordinates right away. So if you go back and see where it says the density is inversely proportional to the distance to the origin, we just do it in parentheses and say that the density, which is, I use a delta. Remind you real quick, the book uses rho for density, I believe. I always check that every semester and it's always the same. So the density is rho in the book, but that becomes a problem in spherical coordinates with a contradiction of variable names. Anyway, density, it's inversely proportional to the distance to the origin. Distance to the origin is just r. Inversely proportional means it's a constant times 1 over r. That's your density function. I mean, you could be more precise, and not more precise, but ridiculously explicit, I guess, and say that it's k. If you're going to put it in rectangular coordinates, you say k over the square root of x squared plus y squared, right? That's almost going too far. But that, you know, we set these up usually in rectangular. Okay. But yeah, so for the density function, it is a function of x and y, but the first thing I'm going to do is I'm going to change it to k over r. And then the y, just to remind you, y is r sine theta, so we'll change that. And then dA is weird also. One of the things we figured out last time is that you can't just do dr times d theta and get an area because theta is not a length. So if you may remember, arc length on a circle is r times theta. In this case, because it's a differential angle, it's r d theta. Bottom line is dA gets an r in it. It's r dr d theta, and that's two lengths multiplied together there, r and dr. And you get a differential area that way. Okay, so we can plug everything in here, and then we'll have to put limits on the integral, which is the most painful part. So y squared, that's going to be r sine theta squared, and then times k over r. And then we're going to have an r dr theta. And then the limits on r. Well, r is 1 as the lower limit, and then 2 sine theta as the upper limit. So r is going from 1 to 2 sine theta. And then theta goes from 5 over 6 to 5 pi over 6. Okay. Now, I am ashamed to say that because we were rest last time, I didn't evaluate very many integrals. I'm going to evaluate this one. But I'm going to do it quickly. So dr is just a function to a function. That sounds very philosophical as far as limits go. It's a differential. It's a limit. dr is sort of a limit. It goes to 0. Remember, these integrals are actually limits. Okay, going on. Here comes, I'm going to do a little bit more simplification before we begin. Let's put the k outside. And we double integral. Maybe a little more space. Okay. So we're going to have r squared. The other r cancels. So we're going to have r squared sine squared theta. Now, okay. The sine square actually is a constant right now, so you could actually smooth that. I'm just to kind of give you the sort of the sense here. You could, if you felt like it, you could say k integral pi over 6 to 5 pi over 6. And you could put the sine square out there if you don't like looking at it. It can't come out any further. But inside here, you've got this integral from 1 to 2 sine theta. And that's your r squared. And then there will be a d theta. Okay. So it's an integral in an integral. Okay, any questions? Don't see anything out there. Let's keep going. I'm just going to leave that sine square there. So you get that sine square theta. And then maybe in parentheses, we're going to have a 1/3 r to the third. Okay. R is going to go from 1 to 2 sine theta. Isn't that horrible? So you got to really be on your integration game if they're going to make you evaluate these. You can see this is all going to be a function of theta shortly. Maybe write a k over 3. Let's get rid of that 1/3. So you got a k over 3 integral from pi over 6 to 5 pi over 6 sine square theta. And then the inside, we've got an 8 sine cube theta. I actually like the odd multiple. Maybe you'll remember. It's nice when you have an odd power on a sine or a cosine. And that looks like it's -1. And then the d theta. Woo. So we're going to have a sine to the 5th. We'll break this into 2 integrals. Whoa, what happened? Pi over 6. 5 pi over 6. We can just do 8. I'll get it to the 8 out here. And, oops. We just get a sine to the 5th theta. And then we got to deal with the sine squared also. So that would be minus the integral from pi over 6 to 5 pi over 6 over sine squared theta. Totally different methods to deal with these two. Any questions? Now, when you have an odd power on a sine or a cosine, you want to think of that as an even power times a first power, and then the even power has to be converted to cosines. So you go like this, you go k times 8 integral, and what you're going to do is you're going to do a 1 minus cos squared theta, and that's sine squared. So then sine squared squared is sine to the 4th times another sine theta d theta is your trick. So right here is your, that whole thing is sine to the 4th theta. Convince yourself of that. And so that all makes sine to the 5th, and you got a pi over 6 to 5 pi over 6. And then the sine square is 1/2 1/2, is it 1 minus cos 2 theta? That's what they call power reduction formula. And I think the k is outside of all of that. Okay. Okay, so here we're going to say u is cos theta. And I think negative du is sine theta d theta. Oops, I forgot my equal sign, pardon me. Okay. Other integral is easy compared to this thing. So you get a k times 8 integrals, don't have the limits yet. So this will be 1 minus u squared squared. With a negative, so I'm going to put a negative out in front of the whole thing. A negative du. And then I got to figure out what cosine of pi over 6 is. I'm hoping it's the same as the cosine of pi. No, it's not. What's the cosine of pi over 6? Is that root 3 over 2? Well, you guys are telling me k over 3. Is there 1/3 out here somewhere? Okay, right. I see the k over 3. These are all k over 3. Thanks, guys. You're very helpful. Awesome. Okay, where was I? Sine is this. So at pi over 6, cosine theta is that root 3 over 2? So you're going to go from root 3 over 2 as the lower limit to the cosine of 5 pi over 6, which I think is negative root 3 over 2. Rule of thumb, if your differential ever goes negative, then your lower limit and your upper limits are going to be switched. So my du is negative on this one, and my limits are backwards. So anytime a differential is negative, that means you're integrating in the wrong direction. That's okay. That's the least of my worries right now. On the other one, we've got a minus 1/2. Let's see if we can evaluate this. So you're just going to have a theta from pi over 6 to 5 pi over 6. And so that's going to be a 1/2. So minus 1/2 sine 2 theta from pi over 6 to 5 pi over 6. I'm hoping those will be the same, so they'll just cancel. Sine's the y coordinate, but it's 2 theta, so you have to multiply by 2. Okay, any questions? I don't have any genius ideas right now. It's k over 3. I just keep brute forcing it, if I can say that. Negative 8. I'm going to leave this as negative, actually, let's make it positive 8. We'll switch the limits. So we'll just go from 8 integral from negative root 3 over 2 to positive root 3 over 2. That changes the sign, so that's why the minus sign is gone. And then I'm going to have to do 1 minus 2u squared plus u to the 4th du minus 1/2. And now I've got 5 pi over 6 minus pi over 6. That's 4 pi over 6, which is, let's say, 2 pi over 3. 5 pi over 6 minus pi over 6 is 4 pi over 6, which is 2 pi over 3. Now, what's the sine of 2 theta? That would be the sine of 5 pi over 3. I guess I don't have the nerve, so it's minus 1/2. I've got the sine, again, 5 pi over 3. Minus the sine of pi over 3. I don't think those are going to cancel. I wish they did, but they're in different quadrants. So One's positive, one's up above and the other's down below. It's not good. Lots of parentheses, lots of parentheses, good heavens. A center pi over 5 pi over 3 right here. This is negative root 3 over 2. This is positive root 3 over 2, but you're subtracting it. So it's another negative. Now here come the rest of the antiderivatives. K over 3. I've got the 8. I'm now going to evaluate. So this will be u from negative root 3 over 2 to positive root 3 over 2. And then this will be minus 2/3 u to the third from negative root 3 over 2 to root 3 over 2. And then plus 1/5 u to the fifth from negative root 3 over 2 to root 3 over 2, like that. Close off that. I'm going to do you a favor right now and just say minus 1/2. Trust me, you're going to get 2 pi over 3, no kidding, and minus root 3 over 2. You subtract, you just get negative root 3, but then it's times another 1/2. So I think I've got a problem with the minus sign. Hang on a second. Okay, so you guys back up. Well, that looks good to me. Oh, I see. So good. So keep going here. So I think we get minus just a root 3 over 2 here. Okay. Okay. So let's see if we can do some of this in our head. This is horrible stuff. So you have k over 3 and an 8, and I think you just get root 3 over 2 plus root 3 over 2, so this is just root 3 minus 2/3. Okay, so when I do root 3 over 2 to the third, I'm going to get 3 root 3 over 8, and that'll be plus 3 root 3 over 8, which is 3 root 3 over 4. Okay. Plus 1/5. Okay. Now if I do root 3 over 2 to the fifth, 2 to the fifth is 32, and root 3 to the fifth, I think, will be 9 root 3. So it's going to be 9 root 3 over 32, but you got 2 of them, and you're adding them, so you're going to get a 9 root 3 over 16. That's just trusting that I didn't screw anything up. Now this is minus pi, those 2's cancel, so I'm going to distribute now, so I get minus a pi over 3 and plus a root 3 over 4. Yeah. And where's the parentheses? Where do the parentheses end? I think I have to put parentheses there. Oops. Okay. Looking for mistakes. I don't see you guys typing any mistakes up here. So look, I'm just gonna keep going. If you find a mistake, I may just pretend like I don't see you. We'll see what happens. Okay, here I get the 3's canceling. 2 goes into 4 2 times. Nothing you can do with that other one. Ugh, that's horrible. 5 times 16 is 80. Actually, there's a lot that you can clean up there, but so hang on, k over 3, I've got an 8, oops, an 8 roots. I think I'll just do some working here first. So I got 8 times root 3 minus just another root 3. Nope, root 3 over 2. And then plus 9 root 3 over 80. These are all root 3's. Oh, the 8's going to be handy in there. Oh, a lot. Yeah, that'll be great. So then I have a minus root 3, sorry, pi over 3, and plus root 3 over 4. Okay, we're going to pound it out now. So this is k over 3. I got 8 root 3 minus 4 root 3 plus 9 root 3 over 10 minus pi over 3 plus root 3 over 4. Okay, getting my magical calculator that does fractions. So, and I'm hoping this is right, but anyway, 8 minus 4 I can do in my head, plus 9/10. Don't really want to do in my head. Plus 1/4. Okay, and so my calculations are k over 3 times 103 over 20 root 3 plus 3 pi over, sorry, plus, sorry, minus pi over 3. And I could look deeply into my notes. I'm not crazy about it. Oh, I didn't do this one in my notes. I did the moment about the y-axis in my notes. And this was the moment about the x-axis. Yep. So that really looks very similar to the moment about the y-axis, but we're going to just assume this is right. Shouldn't be plus root 3 over 2 on the first step of the what? You're telling me that now? Oh, I see. That should be a plus sign, you guys. I do have a plus there. So I think you're talking about this. Oh, I see. Hang on. Here's here, here's 2, so it's negative root 3. I see. Yeah, okay, I see it. Okay, so you're telling me this should be over 2. So I'm going to put this in green, and let's see if you agree with me now. Do you agree with that, Bilal? And that's going to change my final answer, so half a moment. I'm not going to get too far ahead of myself because I want to make sure Bilal agrees with me. No, for what? First step to second step. That's what I was doing. Pi over 3, negative. Okay, now that's a negative root 3 times negative a half, which is root 3 over 2. Oh, I forgot about that other half. So now I'm having to backpedal here and see what's going on here. I see. You're saying this should be a plus right there. Is that what you're saying, Bilal?
I just hope it's not, hang on, it's not refreshing. Yeah, I hear what you're saying. Hang on, I guess my share is frozen. Let's see if it comes back. Exactly. Okay, good. So now we can say we agree. And that just changes the plus to a minus. Agreed? So this should be a minus here. Oop. Okay, so I'll put those in green. Those are all minus signs there. Okay, good. And then we got to redo the math. So so it's not plus a fourth root 3 over 4, it's minus. Hang on. So you see how bad these are? Okay, so now it's 93 instead of 103. So I'm going to erase the numerator on the square root of 3 and make it a 93. Minus the pi over 3. So again, now Bilal agrees. So that's good enough for me. I don't want to hear any more people talking about this problem. It's beautiful. Even ugly children are beautiful to their mother. And I'm sort of the mother of this problem. So don't say a word about my child, because I will get angry. Okay. That's a moment of inertia. It's 7:10. Let's do a real quick discussion about probability. Okay, so R here is the domain of a probability density function. Let's say 2 variable probability density function. Now notice before I was calling it a mass density function. Okay, I'll now say probability density function. Okay, so this is analogous. Oops. So I don't know who stole from whom, but when probability theory was being developed, gosh, I guess, a lot of work was done in the 1800s. And even before then, I know that probabilities for gambling games had been worked out as binomial experiments in the 1700s. So probability has been around, I think, since the 1700s. And at some point, people started borrowing formulas between the physics formulas, so or engineering forms or whatever you want to call them. So when I show formulas for center of mass in a statistics class, that you would see formulas on the mean. So let's go ahead and do a domain. So we're going to do a region inside of R.
So D is a subset of R. Okay, and XY is a random point in R. Okay, a random point in R. Okay, and when I say and I have to give a probability density function. I forgot about that. So I guess we're going to use a rho for this. So because the rho looks like P, which reminds me of probability. So rho of XY is the probability density function at the point XY. I'll just say it's the probability density at the point XY. Okay? And if I do P of D, this needs to be described in words. This is the probability that XY is in D. Okay. And it's just the density function. So basically you do double integral, you add up probability density. It's like adding up mass density where you get mass. If you add up probability density, you get probability. Okay, so you have to do a double integral over the domain D, not the whole region, but a double integral over this region that you're trying to see if XY is in there. So then you just integrate the probability density function over that region. Like that. Okay. P of R would be a double integral over R of rho of X, Y. Yeah, what do you think this is? I'll tell you, XY is bound to its domain. So what's the probability that XY is in R? I guess I could write this out. This is a probability that XY is in R. Question, any statements? 100%. That's right, Bilal. This will come out as the number 1, which is 100%. Okay. What do you, and by the way, this is analogous to mass. So in the physics, we were integrating mass density over the region, and the integral of mass density is just mass. The integral of probability density is total probability, which is always 1. And 1 in probability theory, of course, is the same thing as 100%. Any questions about that? Looks like I'm frozen, so let me see if I can unlock it. Here we go. There we go. Okay, so probabilities always have to add up to 1 in a probability space. Okay, and I guess I could use that word. R is often referred to as a probability space. Sometimes they call it a sample space, but I won't go there. The space from which you sample data. Okay, so x bar, and let's do this as a vector just to be cool about it. So x bar, y bar is the mean vector, or point, if you like. Okay. Now, normally, you know, in physics, we would call that the center of mass, but in probability theory, we would call it the mean. Okay, and so x bar would be the moment, it would be the first moment. Okay, so you would just do a double integral of, now the x bar is the distance to the, x is always the distance to the y-axis. Okay, but the first moment you would have to do my, which uses that x distance, and then you multiply by mass density, no, probability density, rho of xy dA. Okay, you would divide by total mass, but remember total mass is always 1, so you don't, in probability, the total mass is the total probability, so that's always 1. Okay, y bar, also first moment. So you would have to do moments. Y is a moment to the x-axis, so this is actually mx, but we'll just say it's y times the density rho of xy. Yeah. Okay. You're integrating over R, the whole region, to find where the center of mass is, but here is called the mean in a probability space, but it's a vector. Okay.
Quick question, sir.
Yeah.
Is that P or rho?
I used a rho.
Okay.
You mean in the integral?
Yeah, in the double integral.
Yeah, it's a rho. I'm using the notation in the book now. They use rho for the density functions, but the probability stuff is not as important to you guys. So I don't mind going back to the book's notation for probability density, but for mass density, they use rho as well, but it's confusing later. So I use a delta for density, for mass density. Okay. And so these are just centers of mass. It's the same formula, except for the total mass is always 1, so you would divide by 1. And then the only other thing is just these moments of inertia that are interesting because moments, well, let's just call them second moments. Okay, so you would have like about the x-axis. Okay, this is analogous to the moment of inertia, but you do double integral. About the x-axis, you have a y squared distance, and then you multiply by probability density and integrate over the whole region. So that's a second moment, and then about the x-axis. Sorry, the y-axis. The distance to the y-axis is x, so that's what you're squaring. Okay, those are second moments. These are called variance. So this is the variance of y. The other one is the first one's variance of x. Oh, no. Those are y distances. So that's the variance of y, even though y is the distance to the x-axis. And the other one's variance of x. And just as a reminder, standard deviations, and of course, these are analogous to moments of inertia. I need more space.
Okay, so the variances are the moments of inertia in probability theory. And standard deviation from statistics, super important. Standard deviation is the square root of variance. No, I'll just say symbol. Okay. And so that's all from statistics. There's more, as you can see, statistics uses the same sort of theory that we use in physics and mechanics. And standard and statistics gets as weird and abstract as all the stuff we're learning here. And it's a fascinating field and lots of good jobs out there in statistics. Mostly behind computers. Okay, I just want to introduce that stuff. I really don't. Okay, so we're going to add one more thing to the discussion. This is going to go back to the physics material. So it has to do with sort of a rotational analogy to center of mass, and it's called radius of gyration. Okay, so just remember the moment of inertia is like mass times distance squared, and I'll use r for the distance times the mass. And so if you solve this for the radius for r, you get r is the square root, and this will be positive square root of the moment of inertia divided by mass. Okay, so this again is called radius of gyration. And I could be any moment of inertia. If you remember the centers of mass, like for instance, x bar was my over m. So you take the moment, you divide by the mass, and y bar was mx over m. Again, the first moment divided by the mass. Here, you're taking the moment of inertia and dividing it by the mass, but because it's a second moment that involves distance squared, you want to take the square root of the distance to get a distance. So radius of gyration, and by the way, I think they put 2 bars over it, I think, like r bar, I think is what they do. And so the radius of gyration is basically the distance. Where if, let's say where comma, if we concentrate the mass m to a point, at a distance, let's say, to a point, and again at this distance from the axis of rotation, then the moment of inertia doesn't change. So it's just a distance to an axis of rotation that sort of acts like a rotational center of mass. I mean, a center of mass
is a location where if you could concentrate the mass to a point and set it at its center of mass, then all of the moments would be unchanged. The moment to the x-axis and the moment to the y-axis would be unchanged. If you concentrate the mass to a point and locate it at the center of mass, it preserves the moments. And this is like that, but it's sort of a rotational idea. Okay, so that's radius of gyration. I think I'll leave it at that. Any questions?